Hello, in this video we will talk about the basics of artificial neural network in machine learning. And here we will implement a multi-layer artificial neural network from scratch with Python. So although there are many ready-made packages for neural network, so here we want to explain the details of and fundamentals of the neural network. So we will step by step explain the neural network and the mathematics behind the neural network for the training, and we show later examples of digits classification using this module in Python. So here we look at this figure. This is called multi-layer perception, or MLP, a very simple neural network. So here we see there are two layers. So this first layer, so although this is input, we can also say layer, but usually from this layer, this is a hidden layer. Hidden layer is several neurons, because here we have no neurons, but here has a neuron. And here is output layer, also has neurons. So usually output layer has the same dimension for the classification task. For example, if for the digits, there are 10 digits, right? 0 to 9. So this output layer has 10 neurons. And we can define the numbers of hidden layer, the neural numbers. So this is a hyperparameter you can define. So they're called two-layer perception model. So belong to the multi-layer perception model. And here you can see this is for the data coming in. Data, for example, 100 or 10,000 observations, examples. Each example has the feature 1 to m feature, right? For example, digits, they are set in the digits, maybe they have 728 features for one digit input. And this model has odd connections between each neuron and its input feature. So for each observation, there are m features, and m feature has m times the number of neurons in this hidden layer, these connections. So each line represents a connection with one parameter for the weight. And similarly, here is all full connections. So you can see there are many parameters. And each hidden layer's neuron connects to each neuron in output layer. So we write here A because this layer has activation. This layer also has activation. So A means after activation. Because if we do not use activation function, so usually activation function is like a logistic regression or other kinds of. So these kinds of activation function are non-linear. So if they're linear, all the linear functions without activation, they are meaningless, because linear times linear will come with linear. You can also model only the linear data. This is meaningless. So we have to add activation, non-linear, in each layer. So very big model, you can imagine there are many activation of the non-linear. So they can model very complicated data. So this is the basics from data in, then with a linear parameter, weight times the data, then come to these hidden layer neurons. Then after activation, we can get different values from the values before activation. So again, after activation, they also, with the linear parameter weight times together and plus the BS term, reach to the output layer. Then at output layer, we also have activation, nonlinear activation. Then come to the dimension with the labels. Of course, here we did not show the training of the model, because the purpose of the machine learning is to get the trained model. Trained model means we get the best parameter for the weight, because we want to get this parameter to predict the later observations we have not seen. So we get the training data as information for the input feature and its label. Then we train the model to make this prediction as close to this shown label. We know this label. Then we get the parameter, best parameter after training, and we can predict the data we have not seen. Now this is the flow of any machine learning model. So if you want to understand a little bit more, then we can look at this figure. So this is called adaptive linear neural. Actually, this is only one layer, because here output we just use a threshold, and this neural layer we just use the identity. So identity means actually this activation is just the same as we did not do any activation. So this is called net input. Net input means feature times weight plus bias, called net input. So this is sigma summed together before one example. So one example, for example, one digit, we have M feature. Then M weights connected to this neuron. This is only one neuron. We only show one neuron here. Then summation of this multiplication and plus bias term together, this is net input for this observation. So here we does not add any nonlinear, but just identity. This is very called linear neural. This is linear neural, but although this is linear, we can also know what's happening if we use nonlinear. So from this line, for this point, we get the error. So after this linear activation, we get the error using the difference between XY and this value. Then we update, because we get this error, so we can update the parameter of this weight. If the error is very big, so will be updated very quickly based on the derivative of this error or loss function with respect to this parameter. And we update simultaneously for all the parameter iteration. This process will take, for example, 500 iterations. Then we get as close as to the true parameter, which will make the error will be very less. So after the model trained, we get the parameter, then we can predict the label here. Also here activation is just a threshold function, very simple. So multi-layer MLP, we just add the hidden layer and with the, for example, logistic activation function, and we add output layer here, also use a nonlinear function for activation, for example, logistic. But the basic flow of this information is the same. So in this page, we show the mathematical forms for net input and activation. So for one example, so one observation or one digit coming in, the feature, M feature for one digit. Then we have the same number of parameters for the weight and times together. Then we get also, here we just skip the addition of a bias. So because we are interested in the weight, so we just say this is a net input for this observation, for this example, at the hidden layer. Then after we get the net input, we can use the activation function for this net input, for this observation. Then we get the activation of the hidden layer. So we use AH means after activation at hidden layer. So this is logistic activation function. Then we can write in matrix form for all the examples. So we use caps lock for large alphabet. So here for all observations coming in times the weight plus BS term, then we get a matrix form for the input for all observations. And similarly, can get activation of the hidden layer for these observations after we get the net input. Then similarly, we can use this form for the output. So after we get the activation for the hidden layer, then use this value times the weight for the output layer. Then this is T for the transformation, because for the multiplication for the matrix. Then plus the BS for the output layer, and we get the net input for the output layer. So this is the activation of the output layer after we use this logistic function to net input for the output layer. So we look back, this figure may be more clear. So this input there times matrix multiplication for the weight and with the how many observations, and each observation has M feature, right? So the multiplication, then we get net input before activation here. Then after activation, we get AH. So AH's activation then also flow to the second layer or the output layer here with the multiplication of the weight. So this weight is the weight out, so output layer. Output layer times this input of the activation of the hidden layer, then we get the net input for the output layer here before activation function. So we after activation of the net input at output layer, we get activation of the output layer here. Then we can, they have the same dimension as the label, for example 10 digits. So we get here get the 10 probability, for example 0 to 9th probability, and which probability is the highest will get the label number. So this page shows the training process of the neural network. The training means we will update the weight from the derivative of the loss function with respect to the weight. What is the loss function? Loss is the error, because we, from the network flow, for example, at output layer after activation, then we get the probability for each digits, for the probability for the 0 to 9 different digits. But we actually observe only one digit, right? So we compare this output probability with the real value for one observation. Then we sum all these errors for all observation, all examples. So this is the loss function. And loss function then take partial derivative with respect to each weight. So here you can see this is the weight, this also weight, this weight, this each line represents a weight. So we have to update all the weights to get the next prediction will be as close as possible to the real observed label. So you can see this arrow, these two arrows, we want to update the weight when out this line. So this weight, here we only show this weight update. Then can use the mathematical for the derivative you have learned in the calculus. So partial derivative of the loss function with respect to weight, this weight equal to partial derivative of the loss function with respect to A out first, then times the partial derivative of A when out with respect to weight from this rule. But for the other, we can also have similar but not exactly the same form. For example, if you want to, update this, because there are several roads. This is the possible way. This is another possible way, right? And maybe this is also the third possible way and the fourth possible way, like this. But the basics is the similar. We just use partial derivative with respect to this weight. So now we have all the theories ready, then can implement the neural network for labeling the handwritten digits. So you can see this figure shows the tasks of this machine learning architecture. So this is coming in for one observation, one example. For example, here is the 7 digits. This show this label is 7. And we get the input feature of this example. Here is 28 times 28 because this pixel is aligned with a matrix is 2-dimensional array. And we reshape this to 1-dimensional with 784 dimensional input because we want to make the multiplication of the hidden layer, which has 15 neurons, then times together 50 times 784. You can see there are about 40,000 parameters just between the input and hidden layer. And this way is called forward because we from input to the output. Here has activation, also has activation. Then after output we get, for each observation we get 10 number because we have 10 neurons here. And this 10 number actually represent the probability predicted for 0 to 9, these 10 digits. Then we compare with the real label from this data input because we have training data. Training data include the feature and the label. So we know this label, right? So this is called backward because we want to get a loss function. Compare the predicted probability for each number for this 0 to 9, these digits, with the actual label. Because actual label is only one number, 7. So we have to do one job beforehand called one hot representation. So one hot representation actually is transform this number 7 to 0, 1, 0, 1 for the 10 such number. But only one position is 1. So the 7 position is 1, others are 0. So we compare 10 predicted probability number between 0 to 1, this continuous number, right? And with this real observed 0, 0, 1. So this is error or the loss for one observation. So we sum together all examples loss, get the loss function. Then we can do the training process using backpropagation, which we have showed in the previous page for the training process. So next we will show how to implement digits labeling or digits classification using Python. So you can download this file called chapter 11 from this GitHub link. And we have also a website for training for Python and R. So if you are interested in this is a paid course on weekends. Currently we have price for $3 for 2 days on weekends, either for the Python or the R training. So we go to Python So chapter 11, this file, first we import the modules and set a working directory. Then can skip these parts. So we get in the number for the data. This is MNIST data. So this is for the digits about over 60,000 data. We use this function fetch open ML. Quite quick. Then we get the training data using x.value and y label data also value. So we can show the shape of x and y, these two arrays. So the x training data is 70,000 examples and each one has 784 features. So we have to explain that because each digit has about 784 pixels to represent. And here we use the normalization to make this, because the original number value is between 0 and 256, so we make them between minus 0.5 and 0.5. Then we visualize the first digit of each class, for example. So here we show each digit using imshow function for the matrix, for the two-dimensional digits data. So this is the first observation for each digits 0 to 9. Then we show the 25 examples for one digit. Here we use 7. So the different observations for number 7. Then we set the data into training and validation and test. So training, validation is for the training process. We show the errors, how the errors loss will get lower after training for the training data and the validation data. Because validation data is not shown for not see the label, we just compare with after we have trained it. So the test data also not known for the label. Then we set activation function for the sigmoid. Sigmoid is logistic function. And we set a function for one hot for the label, for the Y label, transform from one digit to a vector. Then we set the neural network. Here, there are several attributes for the feature number, number of hidden layer, number of classes. This is same as the output layer. How many neurons? This is the number of neurons in the hidden layer, and this is the number of features. And after we set this initial number, for example, for the weight, for the hidden layer, because this is a matrix with the shape equals to the number of hidden layer for the neurons and the number of features. And for the output layers parameter, the matrix is the number of classes. This is the 10, right? For the digits is 0 to 9, so here is 10 times the number of hidden layers. This is matrix for the weight. This is what we have shown in which is matrix form. Then we define the forward process. Forward process is actually the multiplication of the input feature dot input feature and with the weight matrix from the hidden layer, then plus the BS for the hidden layer. Then we take the sigmoid function for the activation. Then we get hidden layer activation. Then the net input for the output layer is the multiplication of matrix between activation of the hidden layer and the weight matrix from the output layer plus the BS. Then we also use sigmoid for the activation to get the activation of the output layer. Then backward is for training process. So we get the loss. So this is the derivative process, partial derivative process for the parameter. So partial derivative we get, then we return this for object. Then we will create a module. So first we will run this part of the code to create this module class. Then create a module using this class, input feature number, hidden layer 50 and output layer 10. Then we will set the training epoch 50, and here we use a mini batch size 100 because if you use old, for example, 50,000 observation examples, the matrix multiplication will be very compute costly. So we just use a process called mini batch generate. Here we use YAD. YAD means we just get 100 examples after 100 examples from the total training data. So after we get 100 example, then we use the module, calculate the forward process. Then use the loss function only from these 100 examples, loss function, and we update the module parameters with the back process. So here the burden will be lower. And the YAD means we after get these 100, the next time we get another next 100. So this is not generator, for example, 500 each with 100 at one time. Not doing this like this. This is 100 finished, then 100 next. So this is the YAD. Define this mini batch process function. Then we can show here just iterate to show one mini batch is if it is correct. So it is correct for the label 100, for the training data 100. Then we define the loss function. Loss function is return is the one hot. You can see the one hot target actually is a vector. For each observation is a vector, and with the numbers 0, 0, 0, only one place has a 1, right? For 7 digits, for the digits is 7, so only the 7th position is 1. The other position is 0. And the key probabilities is got from the forward process from the neural network process. Here also is a vector with 10 numbers. So each representing the probabilities for each digit. So we take a square and with the mean, because here is the matrix for old observation. So we get the mean loss. called mean loss function. And we define accuracy function actually is the number, how many observed labels equal to the target label. Then we could get the valid, because valid is not in the training data. Because we set the training data 5,000 and 10,000 for the validation, and we will show what's the result of the validation. Just like we do not see this label, and compare it with the real label for the validation, then we can get the accuracy. So we calculate the loss also for the validation data, and accuracy defining. Here we show the result, because this is only for the initializing value. So you can see the MSE 0.3, but only 9.4% of the data are correctly predicted. Then we will define function for the training MSE process. So here all for computing the validation, training, accuracy. You can see the validation also very low for the data for the beginning. Then we define the training process. Training process also we define several empty lists for storing the loss for each epoch, for the training accuracy each epoch, for the validation accuracy each epoch. Then for each epoch, we will get, for each epoch, we will train all the data. So we also get a mini batch first. Mini batch generator gets a mini batch. Then for each mini batch, we will train the model, update the weights using these numbers. Do you remember we get the 4 numbers from the back function in neural network. So we use this information to update the weights for the hidden layer and output layer. So one mini batch 100 examples we will update one time. So for each epoch we will update 500 times for the weights. Then after each epoch finished, we will append this accuracy for the training, validation, and the loss to each in this list we have set here, because we will show it later. So the training process defined. Next, we will train the module. So this is the training. Train the module using the training data, Y training, X valid, Y valid. Also, we set a learning rate 0.1, because when we update the value for the parameter, for the weights, we have times with the learning rate. So now we start training the module. Very quick. We set 50 epochs. So only 1 minute finished. Then we can plot the loss. You see the loss got quite quick, about before 10 epochs. Then would be slower. We plot accuracy for the training and validation. So after this epoch, you see training accuracy and validation accuracy will have a significant gap, but not very big. So which means the module after this process, this epoch, you may have a little overfitting of the model, because the parameter will be update as close as to the observed data. But this observed data, this parameter will not apply so good for the data has not shown. But it's quite good, not so very big. Then we can also, using this model for the test data, 94.5% accuracy. And also, we will show the 25th observations which we get the failure in the prediction. So this is we predicted wrong. So you can see here maybe the reason because this 7 is quite special, or we have not enough training data for this kind of 7 maybe. So also very not so normal for these kinds of input data. I'll say that we have not generally we have not enough data for the training for these kinds of digits, right? So this is the very basics, and we have spent some time on explain the machine learning using very simple neural network. So after you have understand this video, this module for the training, for the mathematical form, and for the forward and back, these two ways, then you can go further to learn more complicated neural network module. Thanks for watching.